Well, good morning. Thank you very much to the organizers for inviting me to stay here today. And I'm talking today about wet forming processes in ceramics, not really slip casting, but also other related processes born from the knowledge of slip casting. I started my studies on slip casting in the 1984 with my Master Science, and my PhD were dealing with slip casting, and my supervisor was Joaquin Requena, who recently died, so I would like to dedicate this talk to him. The contents of my talk are summarized here. I will speak about ceramic processing, a general overview, which has been explained very well in the previous talks. I will speak a little about colloidal stability, although I know that on Friday Paul will speak much more about this topic. I will introduce some aspects concerning slip casting and with some examples for nanoparticles. And on this basis, I will introduce very briefly some other casting-related processes. Well, we all know that advantages of ceramic materials are the high hardness and the good temperature, high temperature behavior of ceramics against metals or other materials. But we have important drawbacks mainly refer to the brittleness and reliability. Griffith, in 1920, established this very simple equation in which established that the fracture resistance of a material was directly depending on the fracture toughness, which is the resistance to crack propagation, and is inversely proportional to the square root of the critical defect size. So, to improve processing or materials properties, we need to reinforce, to look materials with higher K1C, or look for reinforcing mechanisms able to compensate these problems. On the other hand, we can act over processing with a better processing control by means of two ways of actuation. One, to use better starting powders, better control with minor number and size of defects, and better consolidation techniques. Well, to do this, we have seen before in the talk of Professor Gado that we can reinforce materials by introducing dispersed second phase in the form of a secondary phase of particles, platelets, fibers, and so on, or even by designing new microarchitectures like that provided by laminates, FGMs, or coatings. We all know that all the steps in a ceramic processing schedule are interconnected. All defects introduced during one stage are maintained in the following steps. So we have to consider the relationships between properties, processing variables, and microstructure. These interrelations are not direct. We can act on the microstructure by changing the processing variables, and the microstructure determines the properties. But if we can obtain the same microstructure by two different processing techniques, so the relations between processing and properties are not direct. This is a normal schedule for any production process, from the raw material by beneficiation stages, introducing additives, heating, machining to the final forming, and in some very known cases, we start from this situation, but the difference with this example of cooking is that in this case, the raw material has been already produced. And our problem is that we, first at all, after we have all these problems also, but we need to start by producing this raw material from powders. So our process is much more complicated, as stated by Professor Bowen in the previous talk, in which we start from natural or synthetic raw materials that must be conditioned to the next stage of forming a product which will be sintered with a heating schedule. Beneficiation processes include milling, mixing, separation, washing, filtration, and even granulation. And this determines the next step, which is the shaping of a green body. I like to divide the shaping processes into 3 blocks, 3 groups, depending on the content of humidity, content of water in general. Pressing methods, which are usually dry methods. When we introduce more contents of liquids, we are speaking about plastic molding processes, and when we have much more liquid, we use suspensions, and particles are readily dispersed into the liquid medium. In this case, we need to dry the green body we have produced by these methods. Consider, as stated by Paul Bowen, that even in the case of pressing, we prepare granules, controlled granules by freeze drying or by spray drying. And in this case, we also need a suspension, concentrated suspension, to obtain the granules. Well, shaping is necessary because in any device or application, we need a final component with a certain shape and a certain complexity, geometry. These are all the possibilities, many of them, in which every application has different requirements, as we will see now. Professor Gado has made a complete overview of the criteria to select processing conditions, and here is a brief summary in which I state that shaping method depends on a few parameters: quality of the component, the geometry of the piece we want to fabricate, the environmental conditions, and the lot size. If we need a few number of components, we can go to slip casting. If we need to fabricate very huge number of pieces, we should go to pressing techniques. Obviously, for the manufacturer, the main task is the cost of the operation. Well, in the case of slip casting, the process is based on the dispersion of powders in liquid, as explained by Professor Bowen, and the main parameter to control is the colloidal stability of such particles into the dispersing medium. Colloidal processing has demonstrated to provide better properties and high reliability to the materials, and it has other advantages, such as the possibility to obtain complex shapes and tailored structures. In addition, for slip casting, we only need a jar with the suspension and a mold which is of plaster, so the cost is very low in general. This is true if we are able to control all the powder properties, as stated before, and to control the colloid chemistry of the powders into the suspension and the rheology when we use concentrated suspensions, which is the case of slip casting and most of the safe forming processes in ceramics, excluding electrophoretic deposition and a few derivatives. Obviously, the colloid chemistry and the rheology are dependent on the additives, the nature of the powders, the size, and all the aspects treated by Paul, and also on the milling and mixing conditions we have used to prepare the dispersion. Eventually, we must consider the different parameters involved in each of the forming processes we have available. Colloidal stability can be established by controlling the potential of interaction in between particles into the dispersion. In general, the colloidal stability has been explained as a semi-potential, and in particular with the Lennard-Jones potential model, which has two terms, one with the power in the this part of the dispersion, which is the attractive potential, and a repulsive potential in which the power is 12. The potential energy as a function of the distance between particles is plotted in this graph, in which we see that we have two minima. I will explain them later. The stability is achieved when the repulsive term dominates over the attractive one. First of all, we should speak about the attractive potential. The attractive forces are the tendency of two atoms or molecules or bodies to attract each other. These attractive forces are always present and are within the van der Waals forces, in particular the London van der Waals forces, which are always present and are very strong near contact distances. The expression for calculating the attractive potentials is very easy. It depends on the distance of separation between the two particles, the radius of the particle, and the Hamaker constant. To overcome the tendency to flocculation or to attract particles each other, we need to introduce repulsive forces as those in which particles maintain separated each other. We have different mechanisms to promote repulsion, like the electrostatic mechanism, in which the charges are present at the surface and are responsible for the repulsion. Another possibility is the steric mechanism, which is due to the absorption of polymers that cover the particle surface, impeding the surface to touch each other. And finally, electrostatic mechanism, in which the polymers are charged. The electrostatic repulsion can be explained as a consequence of the acid-base reactions that take place between surface hydroxyl groups in water. If we have a metal oxide, we can form acidic species at acidic pH and basic species at basic pH. In water, the ions resulting from water dissociation are those controlling the potential at the surface of the particle, and this is the reason why they are called potential determining ions, and are responsible for the creation of a double layer. If we plot the surface potential as a function of pH, we move from the positive species to the negative species predominance, and there is a point at pH in which the activities of positive species and negative species are the same. At this point, we are in the point of zero charge, in which the net surface potential is zero, as well as the net surface charge density. So, at this point, particles have no double layer and tend to attract each other, and we have free van der Waals to act. So, this point determines the worst conditions for dispersions. At this point, all the suspensions coagulate. The experimental technique we use to measure the stability of a suspension is a zeta potential. Let me show that picture in which we have the particle at the surface. We have a surface potential, and there is a double layer with one monolayer strongly absorbed to the surface, and a diffuse layer moving with towards the medium. We can have here the stir potential as the potentials in the middle of the absorbed layer of counter ions. But we cannot measure this experimentally. We can measure the zeta potential, which is the potential as the shear plane considered as that involving all the first layer of adsorbed ions, even when we have hydrated ions. The point of zero charge of some materials are given here. As we can measure the zeta potential, the measurement of zeta potential with pH are the measurement we have. The value in which the zeta potential is 0 is called the isoelectric point. If we have no specific absorption, the point of zero charge is the same as the isoelectric point. And it decreases as cation charge increases with hydration degree, and depends also on the presence of impurities. In general, we consider that very basic oxides, type M2O, will have very high isoelectric points, or point of zero charge, more than 13 normally. For oxides like calcium or magnesium oxide, the isoelectric point will occur at pHs between 10 and 13 normally. Oxides N2O3, like alumina yttria, have normal point of zero charge of 9, between 8 and 10, and so on. To explain the stability of particles in a liquid medium, we have the DLVO theory, as I have shown before, in which we have this kind of plot for the potential against the distance of separation. We have three characteristics: the potential energy barrier, which means maximum stability of the suspension, primary minimum, where particles coagulate, and secondary minimum, where particles flocculate. Coagulation means that we have touching surfaces. In the secondary minimum, we have particles attracting each other, but there is some intermediate layer impeding the direct contact, so that this is a situation in which we can redisperse the suspension. Well, with the DLVO theory quantifies the potential energy, and we can calculate the total stability of the system by calculating the repulsive term and the attractive term. But it is not the matter in this course. We can correlate stability, colloidal stability, and rheology of the suspensions. In this case, we have alumina suspension with 50 volume%. This means 80 weight% solids, and we see here the variation of particle size, zeta potential, and viscosity of the suspensions as a function of the dispersion content, in this case a polyacrylate-based deflocculant. When the polyelectric is not enough to cover all the surface of the particles, we have a lack of dispersion, and the viscosity is high, and the zeta potential is not so good. When we add more deflocculant, we can reach a minimum of viscosity which coincides with the maximum of the zeta potential. This is the best situation to prepare the concentrated suspension, in which we have full coverage of the particle surface. If we have an excess of deflocculant, we have again a decrease of zeta potential and an increase of viscosity. At the 0 point of charge, we have no double layer, and then the coagulation takes place and particles sediment. We can have also two different kinds of particles. Then each one has its own behavior of zeta potential versus pH. In the intermediate zone, what we have is that this material is negatively charged, while this one is positively charged, so that they will tend to attract each other by strong electrostatic forces. This will be useful when we want to cover one kind of particles by other different particles. For example, for mixtures of submicronic material by nanometric materials, as those presented yesterday by Professor Moya. Another way for stabilizing the suspensions in ceramics are the polymeric stabilization mechanisms. I consider three mechanisms. First one is depletion, in which polymers are free in the medium, but this is only effective if the polymers are in very high quantity, so it's not good for suspension, is when the polymer is a carrier material for the ceramic powder. In general, we consider these steric or electrostatic mechanisms in which the evolution of the potential energy against distance is like that I show here, in which there is no primary minimum because particle surfaces cannot touch each other as they are covered by the polymer chains. We have also the way for quantifying more or less the total potential introduced by steric factors. And the steric stabilization has been shown in general before, but what I want to say here is the recent models for the steric stabilization considering the three domains approach of Napier, in which if the two particles with the attached polymer are far apart, there is no interaction, so nothing happens. When they approach and the distance there is lower than 2 times the total length of the polymer, this means that the polymer chains have been mixed. So this is the interpenetration between the absorbed polymer layers, in which case the free energy has a term, which is the so-called mixing term, and depending on the solvent conditions will mean that it can be a repulsive potential or an attractive potential. Take care with that. When we compress the two particles with force to enter into contact with each other, we have that the polymer chains have reduced the size even below the size of one single polymer chain. In this case, we have the interpenetrational plus compressional domain, in which there is a spring-back effect of the polymer, which tends to separate again the two particles. In this case, we introduce a new term for calculating the steric potential, which is the elastic term. And this term is a spring-back effect, so it's always repulsive term. In the case of electrostatic stabilization, we have the same. At the short distances is the steric effect who dominates, and at long distances the charges are operating and introduce an electrostatic separation mechanism. So this is the advantage of the electrostatic mechanism, and this is the reason why they are the preferred substance to be added to the ceramic suspensions. In this case, we have charged polymers, which are the so-called polyelectrolytes. So in summary, we can deflocculate a suspension introducing potential determining ions, that is the pH, or electrolytes, salts, like in traditional ceramics, often use the tripolyphosphates, carbonates, and so on. We can introduce surfactants, and in the case of charged surfactants, we have also electrostatic mechanism. We can introduce adsorbed polymers to provide the steric stabilization. If they are charged, we have polyelectrolytes, and we mix a steric hindrance at short distances and electrostatic repulsion at large distances. And we can also use coupling agents where adsorption of the polymer and electrostatic interactions are present, are explained yesterday by Dr. Pastor Rubio. Well, the main requirement for slip casting is to have a good suspension. Like in Spain, the telepizza, the secret is in the mass. What we need is to have a perfect dispersion and in a good and concentrated suspension. And then we can select different consolidation mechanisms or forming methods. I want to separate these two concepts. The consolidation can be done by filtration, in which water passes through the permeability of a mold, can be achieved by flocculation or coagulation methods, or even by polymerization and gelation methods. All these consolidation mechanisms are useful for obtaining bulk materials, monoliths. And in the first case, the forming methods are slip casting based methods from the slip casting and the family of pressure casting, centrifugal casting, vacuum casting, and so on. In the second case, the consolidation is achieved by the formation of a network because of the destabilization of a suspension that was previously well dispersed. What we do is to prepare a stable suspension, and then we gel the structure of the suspension. This is a physical gel of the particles. And the processes more usual in this case are temperature-induced forming, short-range repulsive forces, and direct coagulation casting. The third possibility is to polymerize in situ. In this case, we have two possible forming mechanisms depending on the polymerization way. We can promote polymerization by from monomers, just chemical polymerization in the gel casting process, or by changing the temperature, we can promote the formation of a gel, like in the cooking for producing most of the products we consume. This is the thermogelation process. We can also promote gelation in the salt gel process by inorganic hybrid reactions, and we can also consider other techniques in which evaporation has a key role for the formation of materials with two-dimensional geometry. For example, tape casting, which is useful to produce substrates, or dipping an electrophoretic deposition to produce mainly cottons. Well, with this knowledge, we know all the requirements of the powders in the beneficiation steps, and the main requirements are the control of zeta potential and colloidal stability, and their rheology in concentrated suspensions. Filtration is the mechanism in which is based the slip casting process, and it is better seen here. What we have is just a well-dispersed suspension and a mold, permeable mold, normally made by on plaster. The process consists in the filling of the mold cavity by the dispersed suspension, and the draining occurs by capillary forces within the mold. Once a cake is formed in the walls of the mold, when we have the desired thickness, we remove the excess of suspension, and then we have the cake attached to the walls of the mold because it is yet wet. After a certain time, it dries, and the piece is easily removed from the mold. As I said before, the consolidation mechanism is based on a filtration process, that is separation liquid-solid. And the shaping processes we can get from this consolidation mechanism are the slip casting classic methods, the pressure casting, or other variants. The requirements deal with the suspension, high solids loading, preferably higher than 30 volume% solids, high zeta potential, always above 20-something millivolts, low viscosity, it depends in this case, it's more difficult to establish a value. I put here lower than 50 millipascals, second at 500 second minus 1 of shear rate. And the advantage is that usually we perform slip casting in water, but we can do also the same in organic solvents. In this case, to consider the stability of the particles, we must consider that the surface charge is much lower due to the lower constant, the electric constant of the organic liquids, so that we need to increase the surface potential at least 2 times over that in water. The other aspect to be considered is the mold. We need a high permeability with channels, open channels, to allow the migration of water during filtration, and relatively high resistance. This is a limiting problem for industrialization. In general, plaster molds are constructed for conventional slip casting, but in industry for pressure slip casting, the main problem is that plaster cannot support a few megapascals. About 3 or 4 megapascals are necessary for several operations, and then polymeric resins are used. The problem is that the polymeric resins are fabricated by the suppliers of the pressure casting machines, so the cost of these molds is very expensive. The advantage is that also they are prepared for a few thousand operations, so at the end is reasonable, the cost. Well, these are the equations governing the filtration across a permeable mold. The only important here is to retain that the square of the obtained thickness in the cake is linearly dependent on the casting time. Up to a limit, because if we put just the thickness instead the square, what we have is a parabolic behavior in which, after a certain time, we cannot increase the cast thickness. Slip casting is useful for producing short series of several complex shapes, as those I'm showing here, and in this case I present, for example, the typical sculptures of Jadro, sometimes horrible, but in this case, this is the combination of many parts, many cast bodies that are joined together with the suspension, and sometimes the maximum, they spoke to me that they have some special sculpture in which they need 800 molds to fabricate the whole piece, with horses, princes, and so on. We can also produce by sequential slip casting laminates, by casting different materials or different suspensions, or alternating 2 kinds of suspensions to produce ABA composites and so on. And we can control the thickness of each of the layers by controlling the thickness during single experiments of casting rate, casting wall formation rate. And we can produce any kind of microstructure. In the case of nanoparticles, however, we see that the slip casting is not the best route. We have here the barium titanate as an example, nanoparticles. We have studied 2 different nanoparticles with particle sizes of 60 and 45 nanometers, but in this case, powder 2, it has 5% of organics. These are the microstructures, this for the powder P1, and this for powder P2. It's just the contrary one expect from the content of organics. First of all, we need to optimize all the colloidal stability and so on. I have done before, and I plot here the rheological behavior of concentrated suspensions. These are suspensions of 78% with polyacrylate. And we see that the viscosity decreases as the ultrasound missing time increases. And we are able even to reach suspensions with 88% solids that can be cast into a plaster mold. In the case of powder P2, when we introduce ultrasounds, the suspension destroys and the viscosity increases. So it is necessary to calcine the starting associated powder. But we see here the sad agglomerate form with 3-4 units of particles. In this case, with the calcine powder, we have viscosities reasonable for casting and comparable to those obtained with powder P1. However, when casted, we maintain the defects we had in the starting powder, like those granules we observed in powder P1. Although the green densities are not so bad, are 60%. Another example to demonstrate that slip casting is not always the best technique for nanoparticles is the slip casting of alumina silica suspensions. In this case, we wanted to introduce nanoparticles in a matrix of alumina, submicron size alumina, like in the examples shown yesterday by Professor Moya with the colloidal nickel. And the idea, when we use high content of second phase, is to produce an external layer of the nanoparticles surrounding the submicron size particle. And at high temperature, a core shell structure develops, and we can obtain mullite alumina composites in this way. And if the content of nanoparticles is low, what we have is the nanoparticles at the triple points, as the beautiful microstructure shown yesterday by Professor Moya. Well, in this case, we have studied all the processing parameters and so on, but what we obtain at the end is that slip casting promotes high-density materials, but heterogeneous, and some macro cracks appear at the surface. During slip casting, we are not able to control always the filtration because of the large area volume ratio that promotes fast evaporation at the surface with, in contact with air. So sometimes we are not really filtrating, but we are just evaporating and drying. So we need to solve this problem, and sometimes to avoid the presence of dust, of those macro cracks observing the slip casting, we need other processes. We need to improve consolidation, and sometimes the solution goes to gelation mechanism or freezing mechanism. As I said before, the main problem of slip casting is that there is a limit for the thickness of a few millimeters, as stated in the first talk tomorrow. No, in the second, Professor Gado. That means that we cannot produce very thick components. When we obtain 1 centimeter or more component, we must consider that part has been created by filtration, but other part is being formed just by gravity and evaporation. So take care with the density gradients we can obtain in this case. There are other problems of slip casting, that the necessity of producing a big number of molds will require the center of Madrid, as said before, long time for drying. Sometimes they use ovens, other times, like in South America, they use 40 degrees C, and it's a problem for the people, but doesn't matter. There is attack and degradation of the molds. For porcelains, the maximum mean life of a mold is 80 times, while for advanced ceramics, it may be 15 or something like this. Well, this claims the needings for accelerated filtration, and in this case, some processes have been developed, the most important being pressure casting, which has been efficiently used for traditional ceramics, for sanitary ware, and is a very advanced technology born in 1985 or something like this. In 10 years, this became the most important technique for producing sanitary ware. As I said before, we have always deflocculated suspensions with very low viscosity. We can promote the formation of a physical gel if we put the suspension into the secondary minimum with short-range repulsive forces by adding counter ions, impurities. and the structure is formed by their own particles. Another case will be if we go to the primary minimum, in which we have very large viscosity, the pH goes to the point of zero charge, and we have complete coagulation. And in this case, we have the direct coagulation casting developed by Gelcasting. Finally, we can obtain a polymer network, and in this case, we have two possibilities. The thermogelation of polysaccharides, in which the slurry gels on cooling below the gel transition temperature of the polysaccharide, or even by chemical gelation of monomers, and the slurry gels by polymerization with an initiator and a catalyst. After that, we can remove the sample from the mold and drain outside. This is the main advantage of slip casting. During a slip casting, water filtrates, so we obtain from the mold a dry body, but we need 2 or 4 hours to remove the sample from the specimen from the mold. In this case, we can get the sample immediately, and drain occurs outside. But the addition of polymers introduces a very important shrinkage effect, which is between 2 and 10% in the green state. Similar processes are with concentrated suspension. If we add polymers to improve adhesion and flexibility, we have the tape casting processes, which is just used for obtaining substrates of 50 to 500 microns thickness, or we can obtain dipping coatings by dipping into a suspension in this way, and the thickness is controlled by the withdrawal rate. In this case, we get microns of thickness. We can improve the thickness by electrophoretic deposition. I think the time is over. We can produce our tapes, and then we can introduce our green tapes directly on a dipping suspension, and in this case, we have a material coated that can be go to the furnace for sintering. And we can obtain directly materials of alumina coated, for example, with a compatible material like alumina zirconia. And even we can produce by different steps a multi-step dipping to produce graded coatings like those shown here, in which with concentrated suspensions and introducing gel formers, we can have even thicknesses of a few decades of microns. And finally, before thanking you for everything, I want to convince you to come to the next Shaping Conference to be held in Madrid in November 2009. Thank you.